Alright, so this is going to be about CO2 transportation through the body. There's three major ways that CO2 is transported throughout our bodies and eventually out into the atmosphere. It dissolves in the plasma, 5% of that, bound to hemoglobin, 20% of that, and the main way that it is transported is attached to bicarbonate, okay? So these are the three main concepts that I wrote for you to follow as I go through the video, okay? So, for the first way, I'm going to start at the tissue, okay? So here I have my tissue cell, and you can see that I have my CO2 right here, okay? CO2 waiting to get transported out and into the red blood cells, which are these red circles, okay? So, like I said, 5% of it dissolves in the plasma. So, CO2 is simply just going to come right down into the plasma. These arrows mean the same thing. I'm just kind of going along with it. So you see I have my plasma. 5% of it is dissolved in plasma, okay? So now, our second factor bound to hemoglobin, oxygen or CO2 comes into our red blood cell, and CO2 binds with the hemoglobin and forms our carbaminohemoglobin, okay? That's the take-home message right there. So this is our second way that this can happen. Now, a more complicated step, and our main way that it's transported is bicarbonate, okay? Well, oxygen, CO2, sorry, is going to come into the red blood cell, and the CO2 from the tissue is going to bind with water and form carbonic acid. Carbonic acid by this enzyme right here. So this arrow is this enzyme, okay? Now, we have our carbonic acid, and I'm just moving him down here. And he's going to dissociate that extra hydrogen, and it's going to break up into a hydrogen and our bicarbonate, I'm sorry. So this is bicarbonate. Now, what is going to happen is that the bicarb is going to want to leave the red blood cell, okay? So it leaves. So now our cell is too positive. It needs to be neutralized, okay? So what's going to happen is I'm going to introduce our chloride here, Cl, and he's going to come into the cell and neutralize it, okay? This is our chloride shift, okay? And then our other hydrogen is going to be bound with hemoglobin, okay? As like a buffer protein. So that is CO2 leaving the tissue cell, getting into the red blood cell, and making its way to the lung, where I'm going to pass it to my associate, Mr. Lyman, and he's going to take it away. Yeah.
So if you understand all that, when we get to the lungs, it's going to be doing everything opposite. So all those steps that Jeff talked about, we're just going to reverse all of them pretty much. So it's a reverse chloride shift, it's a reverse change in the red blood cells, and then we're going to be CO2, the CO2 and dissolved plasma is going to go back into the alveoli. So I'll walk you through it again just to get for a second time. So as Jeff said earlier, the chloride that came in during the chloride shift is going to leave, and this is when the red blood cells get to the alveoli. This is when we're going to get rid of the CO2. So the chloride leaves, bicarb comes back in, so now the charge again stays pretty neutral in the cell. We're going to go back with the hydrogen to form carbonic acid. Carbonic acid turns into CO2 and water, and the CO2 goes into the alveoli. And this is kind of what Jeff talked about earlier too with the dissociation curve. Remember, high to low. So at the tissues, we're high CO2 concentration and then low in the red blood cells. Whereas at the lungs, we're at a high concentration of CO2 outside the alveoli. We're going to go in. and it's going to be expelled. So then this is the main way we get rid of it, like the bicarb, like your 75% here. So then we go back to the carbaminohemoglobin. That's going to go back to hemoglobin and CO2, leaving back into the alveoli, like we said earlier, dissolved. So why do we care about this? Well, what does this have to do with anything at all? The reason for this is that CO2, well, actually two reasons. CO2 buildup in the tissues is very bad for you. It's an acid in the body. It's fine in the atmosphere. Actually, plants use CO2, but humans don't. We can't do anything with it. So when we get rid of it, if we don't get rid of it, it's going to decrease our pH in the body. If you understand pH and pH acid balance, or acid-base balance, excuse me, you know that any change in pH is going to be very detrimental to tissues. It can ultimately lead to death. So if you breathe long enough in a really small room, you would actually die. So don't do that. So why is the other reason that we care? While we're doing all this, we're exercising, we're walking, our body requires oxygen. So if you aren't getting rid of the CO2, you aren't getting the oxygen from the outside air. So for instance, specifically this one right here, the carbaminohemoglobin, if CO2 doesn't leave hemoglobin, we can't bind the oxygen to the hemoglobin, so then we can't get rid of it, and then we die again. So this is all trying to prevent death.